Hello everyone, we've got the final question now on paper 1 from 2022 for Edexcel. And really important, again, I know it seems like a cliche, but we've got another really important topic here. What we've got is parametric integration, okay? Now, I think that this is a super important formula here to be aware of to learn for parametric integration, okay? So it is that the area, if you've got parametric equations, the area underneath the curve is given by y times by dx by dt by dt. So this is super important. I can't emphasize that enough. And I think depending on which version of the textbook you're using, they may or may not make enough of an emphasis on that. And you're not given it, so you're expected to remember that. So that's the first most important thing. Now, there's a lot going on with this question, as you would expect. It's the last question on the paper, and we've got some tricky kind of trigonometric things. We've got substitutions. There's a lot going on in this question. So I'd say, this is by no means a straightforward question. So what does it say? It says, figure 6 shows the sketch of a curve with the parametric equations x is equal to 8 sine squared t and y is equal to 2 sine 2t plus 3 sine t. The region R shown shaded in figure 6 is bounded by C, the x-axis, and the line with the equation x equals 4. Show that the exact area of R is given by that expression there. Okay, so let's have a look and think about what's going on. Now, there's a really important thing straight away, which is very subtle, and it would be very easy to miss this. Notice that our limits are 0 and 4, but they're given on a Cartesian axis, okay? So in other words, the limits for x are 0 and 4. However, we're integrating with respect to t. So just like we do in integration by substitution, we need to change our limits to reflect what we're integrating with respect to. So we need to change the limits because we've got limits for x, but we want limits for dt. So I like to draw a little table, put my x, put my t in there, and here is the x parametric equation that we're going to be using, okay? The x parametric equation is x is equal to 8 sine squared t. So basically I'm going to divide that by 8 and square root it, and then take the inverse. So you've got the square root of x over 8 and the inverse of that. That's how you get your t. So the first value of x we've got is the 4, okay? So we're going to have 4 divided by 8, which is going to be a half. The square root of that is going to be 1 over root 2. And then when we do inverse sine of 1 over root 2, that gives us pi over 4. So when x is 4, t is pi over 4. Next limit, when x is 0. When x is equal to 0, we're going to have 0 over 8 is 0. And inverse, that square root of 0 is 0. And inverse sine of 0 is also 0. So that one's nice. And in fact, actually, the question shows us that the lower limit remains 0. So it was just finding that pi by 4 as the upper new limit. So that's the first and important thing, one of the most important things to be aware of. Now, let's have a look and substitute into our formula. So our y is 2 sine 2t plus 3 sine t. And our dx by dt, when we differentiate this expression using the chain rule, let's differentiate our x using the chain rule. Well, what have we got? X is equal to 8 times by sine t all squared. Okay, that's another way of writing what we've got. So using the chain rule, we are going to times by the power that's there and lower the power by 1. So that's going to give us 16 sine. And then we times by the derivative of the inner function. And the inner function here is sine. Okay, so that becomes cos. So using the chain rule, our x equals 8 sine squared t becomes 16 sine t cos t. Okay, so that's beginnings there. So let's see what we've got to do now. Well, we can see that we're aiming for, we've already got here now, we've already got now 16 sine t cos t. So that's super useful. Oh, and look, we've got this whole bracket is expanded times by that there. So basically what we're going to get is 3 sine t times by that is going to give us 48 sine squared t cos t. So actually that bit's done. So that bit times by that bit gives us already the thing that we require. So that's no further work is required on that part. Now we need to look at this bit. So we've got now at the moment 2 lots of sine 2t, but you'll notice that in the thing we're aiming for, there's a 4t, and it's a cos, and there's an 8 minus 8. So I feel like somehow we're going to need to use that one of those identities where we have to use like sine squared identity and change it in terms of cos. That's what seems to be suggesting itself to me. So let's have a look and see where we're going to go with this. We've got, remember, to times this 16 sine t cos t by this expression. Okay, so that gives us 16 times by our sine t cos t. We've got the 2 there, okay, and we've got the sine 2t as well. So we've got 2 sine 2t, 16 sine t cos t. So we've got 2 sine 2t cos 2t, 16 sine 2t. Okay, so what I'm saying is that this here is that expanded. Now what I've done is I've regrouped it. I've changed the order in which I've written it, because remember I've got this suspicion that I need to use sine squared and use an identity to change it into what we want. So in order to have sine squared, I need to generate from somewhere another lot of sine 2t. So I've written 2 lots of sine t cos t, because that can be thought of as, that is in fact sine 2t. So now I've got sine 2t times sine 2t, that is sine squared 2t. So I've got 16 sine squared 2t, which is perfect, because using one of the double angle identities, sine squared x is a half minus a half cos 2x. So in this case, we have got sine squared 2t is going to be replaced by a half minus a half cos 4t. Okay. Now, if you have any trouble, let me show you what identity I've used there. I've used the fact that sine squared x is equal to a half minus a half cos 2x. Now you might be wondering, where's that come from? Well, if we want to go back to basics, we can go back to what we're given in the formula booklet, the cos, and we can imagine that both a and b were x. So that would give us cos 2x is going to be cos squared minus sine squared. Okay, so let me just show you what I'm saying there. So I'm saying that cos 2x is equal to cos squared x minus sine squared x. And then we're looking for a version that's to replace sine squared. So we need to replace this cos squared with 1 minus sine squared. So that becomes 1 minus 2 lots of sine squared x is equal to cos 2x. And when you rearrange that to make sine squared the subject, it becomes a half minus a half cos 2x. And that's the identity that's been used there to change this one into this one. It is okay to use it, to quote it directly without deriving it. Okay, so you're not going to lose marks if you don't do this derivation here. So if you go straight from here to here, you're not going to lose a mark. It's all good. However, if you get a bit unstuck and you can't remember what this is, you can derive it from things that you are given in the formula booklet. Okay, and you just need to use that identity for cos 2x in the formula booklet. Okay, well, you'd rather use the addition formulae and then change it into the double angle. Okay, so now we can expand this bracket. So we've got 16 times by a half is 8, and 16 times by a half is 8. And now we've done it. We've got the identity that we were asked to get for 5 marks. Yeah, by no means straightforward, but I think quite fair. I think for an A-star question, there was no, tremendous crazy kind of leaps or things that were a bit sort of kind of beyond the pale or didn't make sense. I think that was a really fair A-star question. Nice, solid. It's on a difficult topic. There's a few things to look out for, that we've got to change the limits because they're in terms of we've got our limits in terms of x, but we need to change them in terms of t. We've got difficult identities to be dealing with. We've got to remember how to deal with sine squared. There's a lot going on here, but it's all fair. I think this is a very solid, fair grade A-star question. Okay, right, part B now. So it says, hence, basically we've got to find out what r is. We've got to do the integration now. So this is pretty straightforward compared to what we've had to do in part A. And this is also really nice because there is like a break point. So if you got lost in part A, you always pick it up here in part B and get some method marks, okay? Even if you didn't realize what the value of A was. So 8 is going to integrate into 8t, and then cos is going to integrate into sine, but remember we need to use the chain rule backwards, so we need to divide by the derivative of the inner function. This, again, I suppose that is a little bit tricky. You've got to, I know students find it difficult to spot when something is going to be chain rule backwards, but this fits the pattern for using the chain rule backwards because we've got an outer function, something squared, an inner function, sine, and the derivative of the inner function. So this could have come from the chain rule. So when we use the chain rule backwards, it turns out to be sine cubed over 3. So we've integrated that now, and we need to just put our limits in of pi over 4 and 0 and evaluate what we get. So we get 8 times by pi over 4 is going to be 2 pi. Then we get 4, this is going to be 2 times by sine of 4t. So that's going to be sine of 4 times pi over 4, which is sine of pi. And sine of pi is 0. Okay, so that one becomes 0. This one is going to be sine cubed of pi over 4. Sine of pi over 4 is going to be 1 over root 2. And then we've got 1 over root 2 cubed, and then we've got to times that by 16, and we end up, that gives us 4 root 2 over 4 root 2. The next bracket is just going to be 0, 0, 0, because when you put in 0, that becomes 0, sine of 0 is 0, sine of 0 is 0. So our final answer is 2 pi add 4 root 2. Okay, really good question there. Very, very nice question for the end of the paper. I hope that you found that helpful. If you found that useful, if you could please subscribe to my channel, that will really help me to keep on producing more videos that hopefully you'll find useful. And thanks for watching, and I'll look forward to seeing you in the next video.